Hi everyone. Today we're going to be looking at the higher level part of equilibrium, so 17.1. We're going to be working through a number of questions together alongside some past paper practice to give you an idea of some of the concepts that we encounter the most at higher level equilibrium. So let's get started then. So this is your first question. So you're given a reaction and you are told that in the study of this reaction, different amounts were placed in a closed container. Equilibrium was established at two different temperatures, and you've got the equilibrium concentrations in this table down here. So that's the preamble to your question. So let's see what they're actually asking you to do now. So that's the reaction from the question. First things first, you've got to write the expression for the equilibrium constant, Kc. So we've covered this in our earlier video, but whenever you write an equilibrium expression, you always want to express products over reactants, and you always express the coefficients to the power of the concentration of either the products or the reactants. So let me show you what I mean. So NO to the power of 2, because that's the coefficient, Cl2 over NoCl to the power of 2. Gibbs. All right, let's have a look at the next question then. So for the next question, you are asked to calculate the value of Kc for each of the two temperatures given. So what I want you to realize is that now you've got a formula to calculate Kc because you've written down the equilibrium expression. So by substituting the values in, you can kind of work out Kc. So for example, if we look at the first temperature, you're going to do this value squared multiplied by this value, and that's going to be your numerator divided by NoCl2. So this value is going to be squared. And that's essentially what I've worked out for you here already. So we're following our Kc expression to find our values. So Kc at 503 Kelvin is 4.5 times 10 to the minus 3. And Kc at 738 Kelvin is 9.2 times 10 to the minus 2. So based on these values, you're now asked to predict whether the forward reaction is endothermic or exothermic. So with an increase, with an increase in temperature, increase in temperature, what you've noticed is that there's also been an increase in the Kc. So increasing the temperature has favored the forward reaction, and this tells us that the forward reaction is endothermic. Because remember, increasing the temperature favors the endothermic reaction, and since that was the forward reaction, we increased our value of Kc as well. Good. So let's look at the next sort of question that you can get. So you've got a reaction here for the hydrolysis of ethyl ethanoate, and then you're told if at a particular temperature you have 1 mole of ethyl ethanoate added to 1 mole of water, and then your reaction is allowed to reach equilibrium and you obtain 0.3 moles of ethanoic acid, what would your value of Kc be according at this temperature? So the first things first is that we know that our formula for Kc is going to be products over reactants. So let me just get that out. These are always a little bit long when it's an organic chemistry question, isn't it? Almost there. Gibbs. So all of the coefficients were 1, so I haven't had to raise it to any particular power. Okay, the next thing to realize, however, is that I only have one equilibrium value. So I've put these values into a table for you to kind of visualize. I've been told the starting amount for both of the reactants, but only one equilibrium amount. And this doesn't help me calculate Kc, because remember, to find Kc, I can only use equilibrium concentrations. So the question is, how can I find the rest of those equilibrium concentrations? And there is a method, so it's called the ICE method. I stands for initial concentration, C stands for change in concentration, and E stands for equilibrium concentration. So the best way to carry out the ICE method is by laying it out in a table. So I, C, and E. Earlier we saw that we had these values here, right? We assume that the products start off with 0, by the way, because at the start of the reaction, you've only got your reactants. So based on the fact that there has been a change here of plus 0.3, I know that for a coefficient of 1, the product has increased by 0.3. And therefore, since C2H5OH also has a coefficient of 1, I can assume that this is also going to increase by 0.3. And the ratio is going to be the same, except the reactants now are going to decrease by a factor of 0.3. So once you work that out, we have our 4 equilibrium values here. And now I can insert these equilibrium values into my reaction for Casey. What you'll notice I've done here is technically you're only supposed to input concentration values into Kc, right? Because of the brackets, they're concentration brackets. And since my question has given me moles, I've tried to show the examiner that I'm also accounting for volume, because we can convert we can find concentration by doing moles over volume. However, since all the volume is constant, you can kind of ignore that. And so it becomes 0.3 times 0.3 divided by 0.7 times 0.7. So your final answer for Kc is going to be 0.18. So always be sure to check whether you've got your equilibrium values before inputting it into the Kc to find out the value. So let's look at a past paper question then. So the question tells me I started off with 1 mole of N2, 1 mole of H2, and 1 mole of NH3. And this was then allowed to reach equilibrium. And at equilibrium, the concentration of N2 is 0.8. So let me lay this out then. So N2 plus 3H2 to NH3, and I'm going to lay it out according to ICE. So I started off with 1 mole for all of them. I can assume that this is the concentration as well, because they were in a 1 decimeters cubed sealed flask, so that's not going to affect my number of moles. So the moles and the concentration are the same here. So I started off with 1, and then at equilibrium, the concentration of N2 is 0.8. Therefore, I've lost 0.2 here in terms of my reactants. And because this is a coefficient of 3, I can assume here that I would have lost 3 times that amount, say 0.6. And since this is a coefficient of 2 and this is a product, I would have gained twice this amount, so 0.4. So this would have been, this will be 1.4 and this will be 0.4. So now let's have a look at our answers. So the equilibrium concentration of H2 is 0.4 and the equilibrium concentration of NH3 is 1.4. Perfect. So don't ever forget to lay it out according to ICE, and always be really mindful of your starting concentrations. Use whatever information that you're given, and don't forget that once you figure out the change for a coefficient of 1, to scale it up depending on your coefficient. So here we multiplied 0.2 by 2, and here we multiplied 0.2 by 3. All right, let's look at our last part of 17.1 then. So in our last part of 17.1, we're going to be looking at the relationship between delta G, which is Gibbs free energy, and Kc. So you can see that Kc is over here. So this is how spontaneity and your equilibrium constant are related. And this is a value from your data, this is a reaction that you can get in your data booklet as well, right? So you've got the formula there. So if delta G is negative, which means the reaction is spontaneous, Kc is going to be greater than 1, which tells us that the spontaneous reaction has produced lots of product, which makes sense. And so our Kc is going to be more than 1. On the other hand, if delta G is positive, which means it's non-spontaneous, this tells us that our Kc is going to be less than 1 because the reaction hasn't occurred, and so we're going to have more reactants than products, and so our Kc is going to be less than 1 and equilibrium is going to lie to the left. So let's have a look at this question then. In our previous video on 7.1, we tackled answering the first part and the second part. So now we're going to look at the third part, which is a bit of higher level. So determine an approximate order of magnitude for Kc using sections 1 and 2 of the data booklet. You've been given values for delta G and for the temperature as well. So let's have a look at sections 1 and 2 of the data booklet. The equation that they have in mind, so we're in 17.1, is going to be this equation, the one that we just saw over here. So let's kind of write that down, minus RT ln K, minus RT ln K, and that's going to be delta G. Okay, so now let's look at what values we can input. So we know that R is going to be the gas constant. So that's going to be this value over here, so 8.31. So I'm going to input that, 8.31. I've been given my temperature, which is 298, and then I've got ln K. And then I know that my delta G is approximately 50. Perfect. So now that I've got that, I can essentially substitute the reaction to rearrange the reaction to solve for ln K. And let's have a look at the mark scheme then. So that's exactly what the mark scheme has done. Rearrange the equation to find ln K. You substitute all your values, and then you get this value for ln K. But remember, that's not your final answer, right? Because you want to find the magnitude of Kc itself. So you take the natural exponent of this value, and that gets you Kc is equal to 2 times 10 to the minus 9. Good. So I hope that's been a useful overview of 17.1. Do have a look at our website for further information on one-to-one tuition as well as our revision courses, and I'll see you soon.